My dear students, welcome back to our channel. In this video, I will be explaining the BCA first semester subject Computer Architecture as prescribed by Osmania University and other universities of Telangana. We will go through the important questions and answers one by one. Let's begin with a quick revision. Unit 5 first important short question is: what is an input-output processor, IOP? An input-output processor, IOP, is a special processor in a computer that handles all input and output operations separately from the main CPU. Think of it like a helper in a restaurant. The chef, CPU, cooks food, processes data, while the helper, IOP, serves the customers and brings ingredients. This way, the chef doesn't get distracted and can focus on cooking, just like the CPU can focus on processing instructions. Key functions of an IOP: transfers data between peripheral devices, keyboard, printer, disk, and main memory. Manages I/O instructions. Reduces CPU workload, improving efficiency. Example: suppose the CPU wants to read data from a hard disk. Without IOP, CPU waits until data is read slow. With IOP, IOP reads data in background, CPU continues other tasks fast. Memory trick: IOP is equal to CPU's personal assistant for I/O. This helps in faster, smooth, and multitasking in modern computers. Next important short question is: to define direct memory access, DMA. Direct memory access, DMA, is a technique that allows peripheral devices, like hard disks, keyboards, or printers, to transfer data directly to or from the main memory without involving the CPU for every byte. Think of it like a fast train delivering parcels directly to your house, while the CPU is free to do other work instead of carrying parcels itself. Key points: faster data transfer because CPU is not involved in every step. Reduces CPU workload. Often used for large data transfers, like reading a file from a hard disk or streaming videos. Example: suppose a computer is copying 1 megabyte of data from a disk to RAM. Without DMA, CPU reads and writes each byte slow. With DMA controller handles the transfer, CPU continues other tasks efficient. Memory trick: DMA is equal to data moves automatically, CPU takes a rest. This is important for high-speed input-output operations in modern computers. Next important short question is: 3. What is cache memory? Cache memory is a small, super-fast memory placed between the CPU and main memory, RAM. Its job is to store frequently used instructions and data so that the CPU can access them quickly instead of waiting for slower RAM. Think of it like a spice box kept on your kitchen counter. You keep the most used spices handy instead of going to the main storage every time you cook. It saves time and makes cooking faster. Similarly, cache memory speeds up the CPU. Key points: faster than RAM. Holds recently or frequently used data. Improves CPU performance by reducing wait time. Example: while running a program, if the CPU needs to access a variable repeatedly, it first looks in the cache. If it's there, cache hit, it gets it instantly. If not, cache miss, it fetches from RAM. Memory trick: cache is equal to CPU's tiny helper storing frequent data. This helps modern computers run faster and efficiently. Next important short question is: 4. What is virtual memory? Virtual memory is a technique that allows a computer to use more memory than physically available in RAM by temporarily storing data on the hard disk. It gives an illusion to the CPU that there is more RAM than actually present. Think of it like a wardrobe and a suitcase. Your wardrobe, RAM, is small, so you keep daily clothes there. Extra clothes go into the suitcase, hard disk. When needed, you swap clothes from the suitcase to the wardrobe. Similarly, virtual memory swaps data between RAM and disk. Key points: helps run large programs on limited RAM. Uses paging or segmentation to manage memory efficiently. Reduces program crashes due to insufficient memory. Example: if a 4 GB program runs on a 2 GB RAM system, the computer uses virtual memory on the hard disk to handle the extra 2 GB. Memory trick: virtual memory is equal to extra wardrobe on the hard disk. It helps computers run big applications smoothly even with small RAM. Next important short question is 5. What is the meaning of memory hierarchy? What is memory hierarchy? Memory hierarchy is the organization of different types of memory in a computer based on speed, cost, and size. Faster memories are expensive but small, while slower memories are cheaper and larger. This structure helps the CPU access data quickly while keeping costs reasonable. Think of it like storing items in a kitchen. Countertop: frequently used spices, very fast, small. Cupboard: everyday ingredients, moderate speed and size. Storeroom: rarely used items, slow, large. Key levels in memory hierarchy. 1. Registers, fastest, inside CPU. 2. Cache memory, very fast, stores frequent data. 3. Main memory, RAM, moderate speed and size. 4. Secondary memory, HDD SSD, slowest, large storage. Example: CPU first checks registers cache RAM hard disk. This reduces waiting time and makes the system fast and efficient. Memory trick: memory hierarchy is equal to fastest near CPU, slowest far away. This concept ensures efficient and cost-effective data access. Next unit 5, Input-Output and Memory Organization. Long questions. First important long question is: explain the organization of I/O in a computer system, peripheral devices, I/O interface, modes of data transfer, interrupts, and DMA. Organization of I/O in a computer system. A computer needs to communicate with the outside world using input-output I/O devices. These include keyboard, mouse, monitor, printer, disk drives, etc. However, the CPU cannot interact with these devices directly. This is where the I/O organization comes in. 1. Peripheral devices. These are external devices used for input or output. Input: keyboard, mouse, scanner. Output: monitor, printer, speakers. Input-output: hard disk, USB drives. 2. I/O interface. The I/O interface acts as a bridge between the CPU and peripheral devices. It converts CPU signals into forms the devices understand and vice versa. This ensures smooth communication without errors. 3. Modes of data transfer. Data between CPU and devices can be transferred in 3 ways. 1. Programmed I/O. CPU directly controls I/O, simple but slow. 2. Interrupt-driven I/O. Device alerts CPU only when ready, efficient. 3. Direct memory access. DMA. Device transfers data directly to memory, CPU free for other tasks. 4. Interrupts. An interrupt is a signal sent by an I/O device to the CPU, requesting attention. Example: printer sends an interrupt when ready for next page. CPU pauses current task, services the device, then resumes. 5. Direct Memory Access, DMA. DMA allows bulk data transfer between memory and devices without CPU involvement. This speeds up operations significantly. Example, reading a large file from hard disk into RAM. Example scenario. Imagine typing a document. Keyboard input via interface. CPU processes data. Output monitor displays characters. Printing printer receives data via I/O interface. If printing a large file, DMA can send data from RAM to printer while CPU continues typing tasks. Memory trick. I/O organization is equal to CPU's traffic control for devices. By organizing I/O efficiently, computers handle multiple devices simultaneously, reduce CPU load, and work faster. This explanation covers peripherals, interfaces, transfer modes, interrupts, and DMA, giving a complete overview of I/O organization. Next important long question is: 2. Describe how an I/O processor, IOP, works and how it offloads work from the CPU. Provide a typical use case scenario. How an I/O processor, IOP, works. An input-output processor, IOP, is a specialized processor dedicated to handling I/O operations in a computer system. Its main purpose is to offload I/O tasks from the CPU, so the CPU can focus on executing programs and calculations without waiting for slower I/O devices. 1. Role of IOP. The IOP manages communication between peripheral devices, like disks, printers, and keyboards, and main memory. It can handle tasks such as reading/writing data from two devices, performing data transfer between memory and devices, managing multiple I/O requests simultaneously. 2. How IOP offloads CPU. Without an IOP, the CPU must manage all I/O operations directly, which slows down the system because I/O devices are slower than CPU. With an IOP, CPU sends an I/O instruction to the IOP. IOP performs the data transfer independently. IOP signals CPU when the operation is complete. This allows the CPU to continue executing other tasks, improving overall efficiency. 3. Use case example. Consider copying a large file from a hard disk to RAM. 1. CPU tells the IOP to read the file. 2. IOP directly communicates with the disk and RAM. 3. Data transfer happens in the background. 4. CPU can simultaneously run applications, calculations, or handle user inputs. 5. Once transfer finishes, IOP sends an interrupt to CPU. This is much faster than CPU managing every single byte of data. 4. Benefits. Reduces CPU idle time. Allows parallel processing of I/O and computations. Improves system throughput and performance. Handles complex I/O operations efficiently. Memory trick. IOP is equal to dedicated helper for the CPU to manage devices. Think of it like a personal assistant. The CPU is the boss, and the IOP handles all the paperwork, I/O tasks, so the boss can focus on important decisions, computation. Using an IOP makes the computer faster, efficient, and capable of multitasking effectively. Next important long question is: 3. Explain the concept of memory hierarchy in modern computer systems. Describe the roles of main memory, auxiliary memory, cache memory, and associative memory. Memory hierarchy in modern computer systems. A computer uses different types of memory to store and access data efficiently. Since faster memory is more expensive and slower memory is cheaper, computers organize memory in a hierarchy. This helps balance speed, cost, and storage size. 1. Main memory, RAM. Role holds data and programs currently in use by the CPU. Speed faster than auxiliary memory but slower than cache. Example, when you open a Word document, it is loaded into RAM for editing. Memory trick, think of RAM as your desk space, everything you are actively working on sits here. 2. Auxiliary memory. Role stores data permanently. Speed slower than main memory but cheaper and larger. Example, hard disks, SSDs, USB drives. Memory trick, think of it as a cabinet or filing system where you keep old documents for later use. 3. Cache memory. Role provides very fast access to frequently used data. Speed faster than RAM but smaller in size. Example, CPU stores instructions it often uses in cache to reduce access time. Memory trick, think of cache as your desktop drawer with frequently used stationery quick to grab when needed. 4. Associative, content addressable memory. Role allows data retrieval based on content rather than address. Speed very fast for searching and matching. Example, used in CPU cache tags to quickly check if required data is already in cache. Memory trick, think of it as a searchable index in a library. You find a book by its content, not its shelf number. Memory hierarchy order. Registers cache main memory auxiliary memory. Registers fastest, smallest inside CPU. Cache fast, small, near CPU. RAM larger, moderately fast. Disk SSD large, slowest. Example scenario. While gaming, CPU fetches instructions from cache. Game assets in RAM. Old game data in SSD. This ensures smooth performance without delays. Memory trick. Hierarchy is equal to fast and small near CPU, slow and large far from CPU. Memory hierarchy balances speed, cost, and size, making computers fast and efficient. Next important long question is: 4. Describe cache memory organization and memory mapping methods. Explain how caching improves performance. Cache memory organization and memory mapping. Cache memory is a small, fast memory located near the CPU. Its main job is to store frequently used instructions and data so that the CPU can access them quickly, reducing the need to fetch from slower main memory, RAM. 1. Cache memory organization. Cache is typically organized in blocks or lines. Each block contains data, the actual information from main memory. Tag identifies which main memory block is stored in cache. Valid bit indicates whether the cache contains valid data. Cache can be organized in levels. L1 cache, inside CPU, fastest, smallest. L2 cache, slightly larger, slightly slower. L3 cache, shared among cores, even larger, slower. 2. Memory mapping methods. Memory mapping defines how main memory blocks are placed into cache. Common methods. 1. Direct mapping. Each block of main memory maps to exactly one cache line. Simple but may cause conflicts if multiple blocks compete for the same line. 2. Associative mapping. Any block can go into any cache line. Flexible but more complex hardware. 3. Set associative mapping. Combines direct and associative mapping. Cache is divided into sets. A block maps to a set but can occupy any line in that set. 3. How caching improves performance. Reduces CPU wait time for memory access. Speeds up execution for frequently used data or instructions. Example, While running a game, the CPU repeatedly needs player position and game physics data. Storing this in cache avoids delays from fetching from RAM each time. Memory trick. Think of cache as your desk drawer for daily use items, RAM as the room you work in, and hard disk as your cupboard for old files. You don't go to the cupboard for every pen. Cache keeps the most used items within easy reach. By organizing memory efficiently and using caching, computers run faster, respond quicker, and handle multitasking smoothly, making the system more efficient and user-friendly. Next important long question is 5. Explain virtual memory, what it is, why it is needed, how it works, paging segmentation, and its advantages and disadvantages. Virtual memory. Virtual memory is a technique that allows a computer to use more memory than physically available in RAM. It creates an illusion for the CPU that it has a large, continuous memory, even if the actual RAM is smaller. 1. Why virtual memory is needed? Programs today can be very large, often larger than the RAM. Without virtual memory, the system cannot run big programs efficiently. It allows multiple programs to run simultaneously without worrying about the size of physical memory. Example, your computer has 4 GB RAM, but you want to run a program needing 6 GB. Virtual memory uses hard disk space to compensate for the extra 2 GB, so the program runs smoothly. 2. How virtual memory works. Virtual memory works by dividing memory into small units. 1. Paging. Memory is divided into fixed-size pages, usually 4 kilobytes. Pages of a program are loaded into available frames in RAM. The operating system maintains a page table to map virtual addresses to physical addresses. If a page is not in RAM, a page fault occurs, and it is loaded from disk. 2. Segmentation. Memory is divided into logical segments like code, data, stack, etc. Each segment can be of different size, making it flexible. Segments also have their own segment table to map to physical memory. 3. Advantages of virtual memory. Run large programs even with limited RAM. Efficient multitasking, multiple programs can share memory. Protects programs from interfering with each other, memory isolation. 4. Disadvantages. Accessing disk is slower than RAM, so performance may drop if page faults occur frequently. Requires complex operating system support. Memory trick. Think of RAM as your desk, virtual memory as a drawer in the cupboard. Frequently used items stay on the desk, RAM, while less used items are in the drawer, disk. You swap items in and out as needed. By using virtual memory, computers feel like they have huge RAM, programs run smoothly, and multitasking becomes efficient and safe.